Welcome everyone, and I hope you had a relaxed break. Have you all submitted the assessment? Assessment 1, the project for structure steel? No issue with the first assessment? Okay, no problem. So today we will introduce the second project for the cold formed steel structure. And as you know, this project is 30% of the course. So if you can look here at the top. So the first assessment was 20%. Second assessment or the second project is 30%. This project will be covering the cold formed steel, and the initial due date is 3rd of November. And the last assessment for this course is the final examination, and it has not been confirmed when it will be held yet. So today we will introduce the second assessment or the cold formed steel structure project. And here under this section or under this tab, we have some useful sources for the project. The first one is the project description, which I will show you now. And then we have the cold formed steel structure link to the standard. We will be using 4600, and also we need to use the wind actions standard 1170.2. So in this assignment, we will go through. We will need to calculate the wind on the shed. So we need to use 1170.2, and then we have some capacity tables for the roof cladding and purlins sections, and also the hollow sections to be used for bracing and other sections. And here is the submission link. Okay, I just have a question for you. Do you want to change the groups for project 2, or you are all happy with the group in the first assessment? Do you want to change the group? No answer. Do you want to keep this group as it is? Okay, no problem. We'll discuss this later. But if you, I will keep the groups as it is for now. Any group that has problem or want to change, just let me know. Okay. Okay. So now let's have a look at the group, sorry, in the assessment details or assessment description. So I will start sharing the PDF file. Can you see it now? Thank you. Sorry guys, I just have a problem. Okay, can you see it now? So our second assignment or our second project is about the cold formed steel design. And in this project, we will be again working in group of 3 students. This assessment will be due on the 3rd of November, 9 a.m. And let's have a look on the project. So in this project, we'll be designing the structural elements, including purlin, girts, and bracing rafter and column and end wall mullion for the cold formed steel portal frame shed with the dimension shown in figure 1 and 2. So we will design most of the elements of this shed, but the first two we will not need to go through the uh, hand calculation and so on. We just will use the capacity table directly. So we will have a look on this later, but actually these two very simple steps to design. We don't need to find the moments and design the section in detail. So for the given span of the purlin or the girth, we can select the proper or the appropriate cross section according to the span and according to the applied load. But the other members, bracing, rafter, column, and end million, we will need to design in detail or find the string action and then follow the procedure to find the cross section. Okay, so the shed looks like this in elevation. So very simple support or sorry, one span, single span frame. The frame is fixed at the base. So this one change compared to the previous project. And the plan of this shed is this is a plan. So we have this is our frame span and this is our shed length. Okay, so we have five frames. So we have four spacings. Each spacing is based on your group number. And we have four sides of wall A, wall B, wall D, wall C. And in the last bay, we have wall bracing and roof bracing. And in wall D and wall C, we have the end wall mullion. And in wall D, we have half of this wall is door to access the shed. Okay, this quickly is the plan and the elevation. We'll see now in details, but just a quick view on it. Some given information about the assignment is roof and wall sheeting to be reasonably assumed. So you can use from the available cladding or roof sheeting for the roof and wall sheeting. The Berlin and girth to be from Lysat Berlin and girth sections. So also we will need to select a suitable purlin and suitable girth. Rafter and columns and mullions will be cold formed steel channel from the Doragal sections. We have to consider that the rafter and columns have the same section because again we have a frame. So to work as a frame, the rafter and column should have close or very similar cross section size. The mullion in the middle here can be different. Okay, the last one is the portal frame to be designed with fixed base, not bent. Okay, the elements that are not included in this assignment are no connection design for this assignment, and we are not designing the footing or the floor slab. The earthquake design also is not included. Okay, the design parameters here. The dimension for each group will be different according to the number of the group. The number of the group should be similar to uh, what you have used in group in the first assessment, and only if you change the group or if you have conflict with the group members, just talk to me privately so we can discuss, and if we need to change the group, we will do that. Okay, so for each group, we have the span L, height of the column or the eaves height, and spacing S, and the roof slope. So all the elements here, height and span and roof slope and spacing are given in this table. So according to your table, according to your group number, go to the table to find the details. For the wind load, because we will need to consider or calculate the wind load for this shed. In this shed, we will, or sorry, in this assignment, we will be using the standard AS 1170.2. Okay, so in this assignment, we will be using 1170.2. Have you used it before? How many of you have used the wind load standard before? Have you used that? Yes, thanks, Michael. So we will be using this standard to calculate the wind load. And in the class today, I will quickly go through it, how to start using if you haven't used it before. So the wind load or the wind data for this shed are given as the building or the shed in the wind region A5, the wind terrain category 2.5, the shield coefficient MS is 0.9. There is no topographic effects on this site, so MT is 1. No dynamic effect, so we can use C dynamic as 1. The average recurrence interval for the extreme wind events are 1000 year. For simplification, we can consider the area reduction factor Ka and the local pressure factor Kl as 1. And also for the door in wall D, we can consider it as broken and open when the critical wind occurs. So in wall D, as you can see here, we have a door here in this part. So in our wind calculation, we will consider this door is open. Okay. So this will affect our calculation a little bit. So we need to consider this in our calculation. The wind direction to be considered. Consider the wind direction from south to north and from west to east and from east to west. So this is the direction to be used, and the north is given to you. This is the north for the building. So this is the north, so we can consider the wind from south to north or north to south, east to west from this side, west to east from this side, and east to west from this side. So we have three direction mainly to consider because west, north to west, sorry, north to south and south to north are almost identical. So we have three direction to be considered in this assignment. Okay, so this is the wind direction given to you. So there is no change in the parameter for wind. So all the groups will work on the same wind calculation. The design codes and the method we will be using in this assignment are 1170.0 for what? What is the use for this for this standard, guys? Do you know? Okay. Do you know Michael, Binhua, Brendan, Wang, Wanyu? Do you know what is the use of this one? No, I mean the first one, 1170.0.0. Yes, 1170.0 for the root combination. Thanks, Brendan. So the root combination to combine the wind and dead load, life load, and so on will be given in 1170.0 for the general principles. The second one is 1170.1. This will give us the dead loads G and life load. This is what we will need in this assignment. And 1170.2 for the wind actions to find the wind load on this shed and the design of the elements and the procedure of design is in 11 and for 600 the cold formed steel standard. Have you all downloaded this standard or not yet? This one is important. You will need to use it in the test as well. So we need this standard for our second assignment. Other additional resources or other resources are the LISAT design capacity tables. We will use this capacity table to design the Berlin and girts, and also if we need to find the self weight of these members. And this is an important note here. You are not required to design this using the first principle. So we will design this using the capacity table directly. So according to the span and according to the load, you can just select the girth and the Berlin. So no need to find the moments and shear and so on these members. The tables are available on the Learn Online course website under the Assessment tab. Other table we will be using are the Duragal design capacity tables. These tables will give us the size and properties of the cold formed steel section and the hollow section. So this will give us the section properties for preliminary design. Because to start the design, you need to assume the members to get the self weight and then proceed to check this section is uh, like appropriate or not. So you will need to use this table to design the Berlin struts and for final checking process. However, as the purpose of this project applies the theory covered in lecture, you are required to carry out the actual design for rafter. So for the other elements, rafter, columns, and end mullions, you will need to use the first principle in for 600. So the capacity tables in the design of beam rafter or the rafter and columns and mullions is just to find the probabilities, the weight or the mass and the inertia Z and so on, but not to select a section from the capacity tables directly. Because as you know, there is two types of design. There's some type of design you just need some information like the span of the member and the load, and then the table give you directly the suitable section for this span and this load. However, to learn the procedure and to learn how to design this, we need to follow the the formulas and the procedure given in 114 600. Okay. Again, in this project, you need to write in the report in your own words, and you need to avoid any plagiarism or copying from previous year's project or from other groups. And on the cover page, please uh, include this table so you can input what is the part of the assignment you completed and who checked that, so that we have an idea about the contribution of each group member about the sorry, contribution of each group member in this assignment. Okay, and just I just want to give you a hint here. For assessment one, I will create the Spark plus form so that you can assess or provide the peer assessment for yourself and for your group members so that we can have the spark factor or RBF to apply to the group mark to convert the group mark to individual mark. Okay, so I will let you know when it is ready so that you can complete it. Okay, so the due date for this assignment is again 3rd of November at 9 a.m. And if we need more time, I will give you some additional time. But the time for this assignment is a little bit limited, so we need to start as soon as we can. Additional information to assist you with the project. Here is some guidelines about how to find the loads and how to design the member. So the design loads or the design loads, the permanent loads should allow for the roof sheeting, Berlin self-weight, and remember that the frame member self-weight will be much lighter than the hot-rolled structures. So what is included in the permanent load, guys? Can you tell me for this type of shed? What is the self-weight should include? When you put it on the software, you need to find the self-weight. Sorry, so you need to find the load on this roof. What is included in this? Self weight. Yeah, self weight. Thanks, Bernard. Self weight of what? What are the elements to include? Yes, roof sheeting, thanks guys, and Berlin's, and what else? And the rafter itself. So the self weight for this roof will include the self weight of roof sheeting and purlins and rafter. The bracing is not considered, Michael, because the bracing is only in on one bay, so we can ignore the bracing. It will not affect much. Okay, so now the self weight will include, or the permanent load will include, the roof sheeting and purlins and rafter. These are the main thing. What else we can include? If you remember, we have insulation and what else? Ceiling and surfaces. So these three also are type of permanent load. Okay, I will not be able to do that. Okay, so these three are not for structure elements, but also are types of the self weight, or sorry, are type of the permanent load on the roof. Okay, so this I will leave this for you to assume. And what is the next loads applied to, or what is the other type of loads applied to this roof sheeting or roof? The imposed action. Where to find the imposed action or the life load? The imposed action on this roof are the life loads. Do you know what is the life load for this one? Do you remember the formula for this life load? Anyone know? Have you used it before? Yes, I will open this standard with you. You haven't used the formula for life load before? Okay, let's open the standard. Okay, so let's have a look on the 1170.1, and this is the latest version. So this standard will help you to find the dead load and live load for any building or for any type of calculation. And for our calculation, we need to find now the imposed action. So the imposed action is in section 3, which is indicating the live load Q. So the load or the imposed action or the imposed floor action, are we designing a floor or a roof? Table 3.1 for floor, so we are not using this one because we are designing a roof. So our live load will come from table 3.2 here. So table 3.2 will give us the imposed action on roof, and our roof is not straight awnings type. So we are designing other roofs because this roof is not or inaccessible roof. So our design, we are designing structure elements, components. So the formula for our roof life load is 1.8 divided by A plus 0.12 and should be more than or equal to 0.25 kPa. Okay, so this is the formula we should be using for life load. Okay, so it is 1.8 divided by A plus 0.12 in kPa. I think you have used this formula before, and if it is less than 0.25 kPa, we should take it as 0.25 kPa. Okay, so this for what? For life load or for the imposed action? The next is what? The wind load. So the wind load will be according to 1170.2. So this is the standard to be used for the wind. And if we open the standard again, so 1170.2 is the standard for wind. and this is the latest edition because there was a recent amendment last year, 2024. So this is our standard for wind. Okay, so this is the standard for wind, and section 2 covering the calculation of wind actions. And if you remember from the steel and timber course or from civil engineering mechanics course, civil engineering techniques course, to find the wind actions or to find the wind loads, we need first to find the site wind speed, V site beta, equal to VR, MC, MD, MZ category, MS, MT. So some of the parameters are given to you in the assignment details. Some you need to find yourself. But to find V site or the site wind speed, we need the regional wind speed VR. And to find the VR, we need the average recurrence interval, which is given to you as 1000 year. So there is some few steps to find the wind action. Then after you find the site wind speed, as you know, what is the next step? The next step is to find the design wind pressures, and this is what we will be using in our calculation. So the design wind pressures rho equal to zero point 0.5 rho air, V design theta squared, C shape, and C dynamic. C dynamic given to us as 1 because we are not considering the dynamic effect on this ship. But this is just a quick hint about the standard 1170.2 we will be using to find the wind loads. Any question, guys, about that? No? Okay, so this was the design loads for the Berlin and design girts. Sorry, Berlin design and sidewall girts and end wall girts. Select Berlin spacing to suit the roof sheeting and member length, then determine ultimate load and select from table. So this step is important as well. So if we go to the course website again, under assessments, if you look under assessment 2, we have the capacity table for roof sheeting and purlins and the hollow sections. So if we open this file here, the roof sheeting, so this is the roofing and walling installation manual from Lysat. This will give us some information about the sheets, and these are the some type of sheets we can use here. So you can assume whatever sheets you want, but the main thing or the main parameter we need is the spacings. So if we look here, this is spacing for what? For the roof, and this are the spacing for for the wall. So this is the maximum spacing you can use for to support this sheeting. So for example, if we are using the first one, for example, custom ORB. So what we need from this one, the first thing we need is you need to specify which thickness you want. So for example, if we use 4.48, so in your calculation, you will need the mass for this one. So how much is the mass for this one? 4.81 kilogram per square meter. So you need to convert it to kilonewton per square meter. Then when you select the Berlin, who support the roof sheeting? Can you tell me? The Berlin. So the Berlin spacing will be selected or decided according to this part because the roof sheeting is supported by the Berlins. So if you look to this type, custom ORB 0.48, the maximum internal spacing, these are the spacings that can be used to support this sheeting. So the internal spacing cannot exceed 11, like 1700. The end spacing cannot exceed 1300. Okay, we don't have a single spacing here, so we have 11 1700 and 1300. So your maximum spacing are limited by these two values if you are using custom ORB, and for each type you have to select the Berlin spacing to satisfy this condition here. Okay, if you use this again for the roof, so for the wall cladding or for the roof, for the wall sheeting, so the limits are here. Okay, so what is the internal and end spacing maximum? To 2700. So you can have girths each to 700 for the wall. Okay, so here the red part is the Berlin spacing, how to select the Berlin spacing. The yellow part for how to select the girth spacing. So actually, the girth and Berlin are almost same concept, but the Berlin carrying or supporting the roof sheeting, and the girth is carrying or supporting the wall sheeting. Do you have any question, guys, about this part? Are you still there? No worries, Michael. Thank you. I just confirming you are still there. Okay, so these are the how to select the Berlin and how to select the girth spacing to shear the roof sheeting and the member lenses. Okay, here one hint here. Usually the two Berlins at the ridge and the Berlin and girth at the eave will have sufficient capacity for allowable axial load combining with bending to act as a strut for the bracing system. However, there is no longer any quick method to check this, and we will not be doing this calculation for this project. So in this case, just select a tube member, add the if and ridge to act as the strut using the design capacity table provided in the on the course homepage. So here, what is the what does this explanation means? For this part, we will have at the ridge, we have like two Berlins. Okay. So at the ridge point, we have two Berlins. So we don't need to check the combined action for this part, and we can replace this two by a circular hollow section or a strut to work as a strut. Okay, so this is the hint here, and also we have same thing here, but we have one Berlin only here and one Berlin only here. So actually, this is not our general case to design the Berlin. We are designing the Berlin in the middle. So our general Berlin will be one here or one here. Okay. So this one or this part and this one on the side are not our general Berlins because they are carrying less load and carrying different steering action. So our focus will be only on the red ones, red Berlins. This is what is meant by this hint here. For the diagonal wind bracing, use steel flat bar as tension or cross bracing. So again, we have two types of bracing. I think I have learned this before, but we will discuss it again in this part or in this project. So we have two type of bracing or two forces on the bracing. If we go back to the plan, we have the diagonal bracing dashed. So the diagonal bracing are under tension. So this diagonal bracing under tension force. So we expect they have less forces. So that's why we will assume them as a small size member. But in between here and here and maybe here in the middle and here and here, these red members are what? Are compression, or we call them struts first because they are carrying what? Because they are carrying compression forces. Okay, so we expect the compression forces to be more than the tension forces. That's why we will assume the diagonal bracing as steel flat bar, but the other one we need to find bigger section. Okay, one last point before we have a break. What are the portal frame design loads? What are the loads and the load combination we are considering in this project? The loads we are considering are, again, G, dead load, Q, live load, and W, wind load. So these are the load considered on this project or on this shed. The load combination we are considering in this shed are two, only 1.2 G plus 1.5 Q and zero point 0.9 G plus WU different cases. So we have different sides or different walls, so we need to consider the wind from east and similar to what the direction we mentioned earlier. So different cases means different wind directions. Okay, where does this load combination come from? From the standard 1170.0. So if we ever open 1170.0, this is the general principle one. So the load combinations, as you know, we have, yeah, Michael, just last part and I will have a 10-minute break, okay? Just finish this one quickly. So the load combinations are given in in 1170.0. Okay, seems like this is the amendment one. Uh, yep. So this is the standard 1170.0. So section 4 is the combination of action we are looking at. So we are focusing on the strength load combination here. Okay. So we are not considering all the strength load combination. We're just considering two of them. The first one is 1.2 G plus 1.5 Q, and the second one is 0.9 G plus WU. So this is the only two combination we will be considering in our assignment. Okay, so these two load combination we will consider. Okay. Okay, so now we can have a break for 15 minutes. So we can meet at 10:30. Is that okay? So we'll see you in 15 minutes or at 10:30. Thank you guys. Okay, let's continue. So again, just a reminder that we don't need to apply all the load combination for this shed. We just need to apply these two. So the first one is the critical for dead load and live load, 1.2 G plus 1.5 Q. And the second critical for the wind uplift or the wind upward, so zero point 0.9 G plus WU. Different cases means we will need to consider different wind directions. So this is for the loads. In the class today, we will have some discussion about how to find the wind loads if you don't know. But after all of that, what we need to do, we need to analyze the frame using the loads we have. So we need to model the frame on space gas or strand 7 if you want. So we need to analyze the frame using space gas. So we need to model the frame and don't forget that the bases are fixed, not bent. And we need to assume sections for the column and rafter. So then we will run the model to get the bending moment diagrams and shear force diagram and reaction and forces and so on. So the moment may be something similar to these cases, not same values, but the same shape. So this is the fixed base. So in this case, on the fixed base, we will have bending moment. So this is the bending moment shape for the first load combination 1.2 G plus 1.5 Q. And this is the bending moment for the load combination 0.9 G plus W for the external case, for the external wind case. And 0.9 G plus W internal also will have something like this. So this is just some guidelines or some overview of the moment shape that you may have in your model. Then the main part or the part related to our course, the cold formed steel design. So the main part is column. We start with column design here. So the column will be designed as beam column, remember? So you will need to design the column for axial compression alone, like we need to design for axial compression only, then for bending only, then for combined axial and bending. So Ix for the column will be determined using the analysis using gamma alpha A and alpha B to get K for this waveframe. Sorry, this is Lx, not Ix, sorry. Lx is the buckling length in X direction. So the buckling length Lx determine this from analysis using gamma A and gamma B to get K. Do you know this part? What is K? And what is gamma A and gamma B? So L is the buckling length about X, about X axis, or the buckling about X. So I just have look on it. So maybe we go back to the standard again to show you. We should have used this in our first project to find the value of K for the column. Now let's have a look on it here. Okay, if it is not in the cold format steel one, so we need to use the steel one, the structure steel one. So let's have a look on it. Okay, so I think somewhere here. Yep, this one. So for the member and frame, to find the effective buckling length, KE, we need to use gamma 1 and gamma 2, or gamma A and gamma B. So if the frame is braced, so we use this chart. If the frame is unbraced, we need, or sway member, so we need to use this chart, where gamma 1 and gamma 2 are the stiffness ratio at the two ends of the column. So gamma is equal to summation I over L for the column over summation beta E times I over L for the beam. This if the column is connected to beam at the top and at the bottom. And if the column is connected to the base, so if the column is been connected or not rigidly connected, so gamma is what 10 for fixed footing, or for rigidly connected to the footing, gamma is 0.6. So we go back to our assignment. We need to find gamma A and gamma B, or gamma 1 and gamma 2 to find K for the sway frame, because this frame is sway frame. Ly will be the girder spacing interval if the external flange is in compression. I is LZ or the buckling about Z will be the girth spacing. For second part of the column design, we need to consider the column as bending, as like under bending only. So we will use C equal to 1 because it is a beam column. Cm equal to, we can consider Cm as 1. The bracing interval, think about the compression flange and where it is restrained against lateral buckling, and it will be similar to Ly in the first bar. So you will need to consider the column as beam and then find the buckling or the effective length for the beam. And you can take Cm in this case as 1 for simplicity. Then the third step, we need to check the combined axial compression and bending. Then number 4, check for shear. And this frame might be under tension. The column might be under tension because if we look here, we have some uplift loads. So if we have uplift load, so you can see that the reaction is dragging. Uh, sorry. Thanks, Michael. Sorry. I just open another part. So where we stopped at? Can you tell me? So the second part, sorry to repeat this part again. So the second case for the column is to consider the column as beam, or we need to design for moment only. So for moment only, we will consider Cm as 1 for simplicity. You know Cm? Cm is the factor of the curvature to find beta m. So we can consider it as 1 in this case. And to find the buckling length L for or the effective length for the beam, you will need to find the distance between the bracing so that to know what is the effective section or the effective length of the beam under this moment. So this step 2. Step 3, we will check the combined bending and axial compression. All this will be discussed in the coming lecture, but just a quick hint because it is similar to the concept of structure steel member, but we will use the formulas for cold formed steel. Then we need to check the shear for the column on the column. Then after that, we need to check the column in tension due to the uplift, if any. So if you look here, in this case, or in this case, the wind uplift. So the wind uplift will cause what on the columns? Will cause tension reaction like this one, or up like dragging reaction. This dragging reaction will cause tension on the column. So this column and this column might be under tension based on your calculation in this case and also in this case. So what you will need to do is you need to check the tension. If there is any tension, and if we check the tension, so we need to check the combined bending and tension. So this column will be designed like one time for axial compression only, one time for bending only, one time for combined axial and bending, one time for tension, one time for axial and tension. Sorry, tension and bending. So might be designed for 5 cases. For the rafter design, we need to check the knee and ridge for each load case. So knee and ridge means this is a ridge point and this is a knee point. So this means we need to check the moment at these 2 points for each cases because we expect that the maximum positive moment will be at the ridge and the maximum negative moment will be at the knee joint. Ignore the, this is also one important one. Ignore the minor axial load on rafter and check only for bending and shear. So the rafters are only designed or checked for bending and bending moments and shear loads. So no axial load on the rafter. The bracing interval, Berlin spacing if top flange in compression and distant to first Berlin bust contraflexure point or fly brace interval if bottom flange is in compression. So as you know, again, we are designing 2 cases for the moment. One case is what? The positive moment. One case is the negative moment for the rafter. Okay, for the positive moment, the top flange is under compression. Here, top flange or our critical flange under compression. Or our top flange is under compression. However, for the negative moment, our bottom flange is under compression. So our calculation will be based on the or our critical unsupported length for the beam will be based on which flange is under compression. We will need fly bracing at or near the edge, the ridge condition. The ridge point. So this all uh, are few tips to consider when we are designing the rafter. For the end wall million, we will design as simple beam and bending. So we will design it as simple beam and bending because the end wall million will be subjected to uniform wind load. So the wind load will cause bending moment on the mill in the mullion. Okay, so we will consider the end wall mullion as simple beam and bending because it is supported at the rafter at the top using the rafter and at the bottom using the floor or the base. For inward wind load, compression outer flange restrained by girths. For outward wind loads, compression inner flange will probably need at least one fly brace. So again, we have for the Molin two cases, one for inward and one for outward wind. For inward wind, the girths will be our restraint. For outward wind, we need something from inside to support it, so we have the fly bracing. Other items to complete the design. The remaining items to be considered to complete the portal frame design, which are beyond the scope of project, are connections at the ridge and the knee, column-based design, footing design. All these are not considered in our project, so we don't need to go through this part. Some sheds will also have the situation of adjacent door openings, leaving an unrestrained column between them. The most desirable solution in this case to use a box section for the column. So in some cases, we have some columns without any restraint because of the door openings. So in these cases, we may or we have to use a bigger size or a stronger section for the column, so we can use box section. But this is not our case, so we don't worry about this one. And here, what is the difference between fixed base and bend based? If bend based columns were used, the bending moment at the knee location would be considerably high, as this is the critical design point for both the members and the connection. The saving on base plate size and holding down bolts don't justify the larger column and rafter and knee connection required. Hence, fixed base column with either embedded columns or four bolt base plates are routinely used for cold formed sheets. This is also one explanation of why we need the fixed base over the bent base. Because in the fixed base, we just focus on the column here. So if this our column, this is the moment on a fixed base column. Fixed base. But in on a hinged base or the bent columns, this is the moment on the column and the on the bent base. Okay. So what happened to the moment here? The moment here is, if we just to justify the section, the moment a little bit, the moment here, the moment here was higher on the on this point. So here we are considering the moment here and here. So the moment in this case is higher. Okay. So the moment on the wind base at the top is higher compared to the fixed. So that's why to reduce the moment on the base, we prefer in the cold formed steel to have a fixed base rather than bin base. Okay, so fixed base with either embedded column or four bolt base plates are routinely used for cold formed structures because the moment on the top of the column is smaller compared to the bend base. Okay, and here is the detailed marking guide for this assignment. So the wind load part will have 4 marks from 30. The Berlin design and selection is 1 mark. The girth design and selection 2 marks because we have two type of girths, one on the side wall and one on the end walls. This two will be different according to the wind on each wall. And then we have the bracing loads and design 4 marks. So 1 mark for the loads on the bracing and 2 marks for the strut design and half mark for the design for roof and wall bracing. And roof and wall bracing means what? Do you know? Here we mean here the bracing under tension. For the strut, we mean the bracing or the compression. Strut under compression and the bracing under tension. Frame loading and analysis using space gas or strand 7, 2 marks. Rafter design, 5 marks, 1 for section capacity, 2 or 3 for positive, negative member moment capacity, and 1 for the shear capacity. For column design, 6 marks, second order effects, section capacity with combined effects, member capacity, shear capacity. End wall mulling, design 4 marks, 1 for section capacity, 2.5 for positive and negative member moment capacity, 0.5 for shear capacity. Report structure, 2 marks for the clear writing and drawing and indicating individual contribution in the report. Okay, this again will be due in 3rd of November and we may extend for a little time to give you more time for it. Okay, do you have any question, guys, for today? All good? Okay, thanks guys for attending today and I will see you in the lecture very soon. Thank you.